Okay, welcome to lesson 2 for Calculus 1000. Topic for today's lesson is section 1.5 on inverse functions. And this is a two-part video series for today's lesson. Now, in order to construct and to define the inverse of a function, we first need to define what it means for a function to be one-to-one. A function is one-to-one if it passes one of the following tests. So one of the tests is that f of a does not equal f of b unless a equals b. One other way of saying that is that a horizontal line placed at any y value on the graph will not cross the curve more than once. So if you put those two things together, you want a consistent requirement for a function to be one-to-one. It is that every y value that the function takes only occurs for a single value of x. You can't have two x values giving you the same y value, else the function is not one-to-one. An alternative way to view the requirement for a function to be one-to-one is to look at functions that are either increasing or always decreasing. And in either case, if you try to draw a graph of a function that's always increasing, so as you increase x, the y value increases, or you draw the graph of a function that's always decreasing, so as you increase the x value, the y value decreases. In either case, such a function will pass the horizontal line test. Thus, such a function is one-to-one. And we'll use that in a bit. We'll use those two properties later on. Okay, what about pictures? So can you look at the picture and tell immediately if a function is one-to-one? The answer is yes. So look at the first graph, the one on the top left. Take a horizontal line, so a line running left to right, and place it at any y value above 0. And you'll see that the line crosses the curve more than once, crosses twice. So the top left function is not one-to-one. It fails the horizontal line test. It gives you the same y value for two different x values. The graph to the right of that, however, is one-to-one. No matter where you put a horizontal line, it'll cross the curve at most once. So it is one-to-one. It passes that test. Bottom left, this is an increasing function, and all increasing functions will pass a horizontal line test, and you can play with this if you want. Put a horizontal line anywhere, it's going to cross once. So it is one-to-one, and the last one is catastrophically not one-to-one. If you pass a vertical line or pass a horizontal line at any y value between -1 and 1, that horizontal line will cross the curve an infinite number of times. Because this is a sine function, and the sine function is periodic. It keeps repeating that wave pattern. So not one-to-one. If a function is one-to-one on either its entire domain or in a subdomain, then we can create what's called an inverse function on that domain. And the notation is unfortunate. We can't get around it, we have to use it. Notation for an inverse function is f to the power of -1 of x. And I call it unfortunate because you may be tempted to think that f inverse of x is the reciprocal, 1 over f of x, and it's not. They're completely different beasts. So be on the lookout for those types of notation problems. So we'll come back to that when we get to inverse trig functions. Okay. So I don't really want to read this paragraph. You can read it if you want. I'll pick it apart a bit. The first sentence says that if a function is one-to-one and it has domain D and range R, then the inverse function will have domain R and range D. That's how you could decompose that sentence. The inverse will exist only if and only if plugging an output of f of x as an input for f inverse of x gives you a single x value. Now, if you play a little bit with the definition of an inverse function, then one feature of all inverse functions must be the following: that if you plug a function f of x into f inverse of x, you have to get x back. And if you plug f inverse into the original function, you should also get x back. What this feature is saying is that an inverse does the opposite of the original function. So let's say f of x takes a number, x, and cubes it. Well, you want a function that does the opposite for the inverse. You want a function that uncubes. So that would be a cube root. So those are opposite functions. They're inverse functions. And if you put them back to back, if you do f inverse of f of x, so f inverse, I said, was cube root, f of x, x cubed, that's x to the 3 over 3, which is x to the 1. So that pair of functions, x cubed and cube root of x, they have that inverse function property. How do you construct them in general? So if I gave you a function f of x and told you it was 1-to-1, or you could establish it was 1-to-1, how would you find the inverse of that function? So here's a recipe, and sometimes it's easy to follow the recipe, sometimes it's somewhat complicated for a particular function. What we do is we start by writing y equals a function. Then, this is the hard part, rearranging to isolate for x in terms of y. Once we have that step done, it's essentially very simple afterwards. We then take that expression and swap every x with a y and every y with an x. So interchange the x's and the y's. And then that's our answer. We just say y equals whatever we have for the stuff that's all the x stuff. Well, that's our inverse function. That's f inverse of x. So let's see if it works. Let's do an example, and then we'll test whether or not it actually does what this recipe does, what it's advertising to do. So the graph of this function, if you want, you can go to Desmos. If you Google Desmos, it'll come up with a link to some software that lets you graph functions fairly easily. If you make a graph of this, you'll see that this definitely passes the horizontal line test. So it is 1-to-1, so it has an inverse. The way we'll find the inverse is by using that recipe. First step of the recipe said replace, or not replace, but say y equals f of x. So y is equal to x minus 4 over x plus 4. Step 2, we want to rearrange and get x by itself. The first step in doing that is to multiply both sides by x plus 4, also called cross multiplication. So if we do that, we get this now. Y times x plus 4 is equal to x minus 4. I'm going to distribute the y into the brackets, so I have x times y plus 4y equals x minus 4. Then I'm going to group the x terms together and group the y terms together. And it doesn't matter if you move stuff left or right. I'm going to group all the x stuff together. I'm going to move the xy to the right, and I'm going to add 4 to both sides. So 4y. And the point of this is to get every piece with x on one side. So 4y plus 4, adding 4 to both sides, is equal to x minus xy, subtracting xy from both sides. Then on the right hand side, I'm going to common factor an x out. So I have x times 1 minus y. Then, since the goal of all of this was to get x all by itself, I'm going to do that by dividing both sides by 1 minus y. So I have 4y plus 4 on the left divided by 1 minus y. Now we're almost done. That's the hard part, getting x all by itself. Now I'm going to replace every y with an x, and every x with a y. Just swap the variables. So y is 4x plus 4, 1 minus x. And one more step, we state that that's the inverse. F inverse of x is 4x plus 4 over 1 minus x. And you should not trust this. You shouldn't trust it because we haven't tested it. How do you test this? So how to confirm you didn't make any mistakes? And it really isn't a proof. It's less than that. We're going to plug some numbers into this function, f of x, and we're going to plug the result into f inverse of x. So you can do it the other order if you want. It doesn't matter which order you do this in, but I'm gonna pick an order because you have to pick something. So we take an x value, we plug that x value into f of x, and I'm going to take that output and plug that into f inverse of x. And what has to come out, if this is done properly, is what has to come out is x, the original input. So f of x does something to x, f inverse undoes that operation and giving you the original input. So I'm going to choose, let's see, I'll pick -2 because I don't want fractions, and I'm pretty sure that won't give me a fraction. So I'm going to plug that in f of x, so f of -2 so I have -2 minus 4 over -2 plus 4, so -6 over 2, which is -3. Then I'm going to plug that into f inverse. So f inverse of -3. And I want to get -2 back. If I don't get -2 back, then something's wrong with the construction on the left-hand side. So f inverse of -3. So that's 4 times -3 plus 4 over 1 minus -3. So -12 plus 4 over 1 plus 4. Oh, sorry, 1 plus 3, what am I doing? 1 plus 3, getting ahead of myself. So that's going to be -8 over +4, which is -2, as required. I just chose that at negative. There's nothing special about -2 other than it's a number that results in not creating a fraction. You could also choose x is equal to 0. It's another number that won't create a fraction, and there's a whole bunch of other ones like, well, don't pick -4. Let's see. -8 will work. There's a whole bunch. X equals -8 will also not give you a fraction. And if you wanted to, you could even pick one with a fraction, like plug 1 in for x. Get your output from f of x and plug that output into f inverse and make sure you get the original x value that you plugged in the first place. What you could also do, if you like algebra, if you like manipulating expressions, is take the entire f inverse of x, the 4x plus 4 over 1 minus x, and plug that in for x in f of x. So work through all the common denominator stuff and then dividing a fraction by a fraction, work it all out, and if you do everything right, you will get x at the end. We'll do more of those later. At least one more example, a little bit of a tougher one. Now, there is a particular pairing of functions that share an inverse function relationship. And that pairing that we're going to talk about next is the pairing between exponential functions and log functions. So we'll recall from lesson 1 that an exponential function b to the x is increasing, so is exponential growth if the base is larger than 1, and is decreasing, so exponential decay, if the base is between 0 and 1. So we have a function that's either always increasing or a function that's always decreasing. That means that for such a function, so for exponentials, there must be an inverse. So the f inverse exists for any b to the x. And the name of the inverse of an exponential function is the log function. It has the following feature, that if we define the exponential function y equals b to the x, then to isolate for x, we need to write it as x equals log base b of y. The log function is defined as the function that does this, the function that does the opposite of the exponential. We could have also started with logs and said that y equals log base b of x, and then said, well, what's the opposite of a log? Well, it has to be an exponential, so we would isolate as x equals b to the power of y. And because the domain and range flip between a function and its inverse, we know that the domain of the exponential function is the entire real number line, r, so all the numbers from minus infinity to infinity. We can plug in any x value we want in an exponential, but the range is only from 0 to infinity, because an exponential function cannot spit out a negative y value. If you put a negative x value in, you get a decimal, you don't get a negative. It also can't give you 0. Only in the limit as x goes to minus infinity will the function b to the x for some b larger than 1, only will you get 0 in that case. But that a limit isn't a function evaluation. And for that reason, for the reason that we can't get a y value of 0 for a particular value of x, we put a round bracket around the 0. Okay, so an exponential function has that domain and range, and that means the log function will have it flipped. The domain of a log function goes from 0 to infinity, and the range of the log function is minus infinity to positive infinity. I should write that down. R is the set of numbers from minus infinity to positive infinity. All the real numbers. Real number line. Alright, we'll do more stuff with logs and what I'm going to show you here. But as a kind of review, as a reminder of some basic log operations, for an expression log base 5 of 1 over 25, what we want to have access to simplify this is something called the cancellation law. And there's actually two cancellation laws. The first cancellation law says that log base b of b to the power of a equals a. And actually I won't use a, I'll use x, so it matches up with the notation we've already been talking about. It's the inverse function relationship. We do something to x, we exponentiate it, and then we log it. We undo that thing, we get x back. And the other order, this is for all x, the other order is a bit trickier. If we take a base b and raise it to the power of log base b of x, we'll also get x back, but only for x greater than 0, because we can't plug negatives or 0 into a log function, and the cancellation law doesn't fix that. In order to simplify these two expressions, we're going to have to exploit the cancellation laws. So the first one, I want to be able to write this as log base 5 of 5 to a power. And if that can be done, since 25 is 5 squared, and 25 downstairs, instead of upstairs, can be written as, instead of 5 to the 2, 5 to the negative 2. Negative powers, recall, mean bringing the term to the denominator. Then with the cancellation law, we can cancel log base 5 and just be left with the power, negative 2. The next example takes a little bit more work, and there's a variety of ways you can do this. I'm going to show you one way. Well, before showing you the trick, I want to write this as log base 8 of 8 to some power. So I'll put a little box there and fill in the box off to the side. I can write 4 as 8 to a power. So 4 equals 8 to some power. I'll call that power x because that's usually what we do. I don't know what the x is. The trick, I'm going to write 4 as 2 to the 2. I'm going to write 8 as 2 to the 3. You may have done this in the functions course or in Math 0110. So 2 to the 2. Now we use exponent laws on the right hand side. A power to power. Powers multiply, so 2 to the 3x. Now we have 2 to a power is equal to 2 to a different power. The powers must be equal. The bases are the same. Powers must be equal to each other. So 2 is equal to 3x, and that means x is 2/3. So that's what goes in that box there. And think about what that's telling us to do. Power 2/3 means take a cube root and then square the result. So 8 to the cube root is 2, and then 2 squared 4, we get our 4 that we started with. We can use the cancellation law, cancel the log base 8 and 8 to a power, and we're left with the final answer, 2/3. And there's other ways of doing this, but just wanted to use a method that follows the cancellation law. And stated formally again, I already wrote it, but here it is in typed format. Cancellation law, if you take log base b of b to the x, you get x back, and if you take b to the power of log base b of x, you get x back, with that second one having a restriction on the domain. That you can't plug negatives into logs, and the cancellation law does not allow you to work around that. Now in lesson 1, I briefly talked about exponential functions and reminded you about exponent laws. If you take each of those exponent laws and you translate it into language of logs, then you get the log laws, or the properties of log functions. What I'm going to do is I'm going to write down for each of these rules, or at least rules 1 to 5, what the corresponding exponent property is. Kind of demystify these a bit. So this first rule, log base b of 1 is equal to 0, looks like it's a separate thing you have to memorize, but it really isn't anything other than this. If you write this as exponentials, this restated in exponential language says that a base b to the 0 is equal to 1. So something to the 0 is equal to 1 is not a shocking statement. Second log property, log base b of b is equal to 1, also not shocking. If we rewrite it in exponential language, it says b to the 1 is equal to b. So like 5 to the power of 1 is equal to 5. Again, not shocking. You can also connect this to the cancellation law. How is as follows. Log base b of b equals, I'm going to need that space, log base b of b to the power of 1. If we don't have a power on something, we can always put a power of 1 on it. And then the cancellation law gives us our 1. Okay, rule 3. This is a translation of the following log property, or the following exponent property, that b to the m times b to the n is b to the m plus n. It's a direct translation of that rule. You may be able to guess that the one below it, log base b of m over n is log base b of m minus log base b of n, is a translation of this rule, b to the m divided by b to the n is b to the m minus n. So if you translate that rule from exponent language into log language, you get rule 4. Rule 5 is a restatement in log language of the following property. If you take b to the m and raise it all to the power of n, that's the same as b to the m times n. Power to power of powers multiply. And then the last rule, rule 6, is kind of a combination of rules. And instead of connecting it to the exponent rules, I think it's more useful to tell you exactly why someone would use this formula. So on the left-hand side, you have log base b of m. And you're converting it into log base c of m over log base c of b, and then you ask, where did c come from? Like on the left-hand side doesn't have any c in it, and now suddenly c has appeared. And what that means is c is your choice. It's up to you. You pick anything you want. So maybe you start with a base that you can't do anything with. Like if you want log base 3 of 7. For some reason you want this number in decimal form. So you take out your calculator and you're like, okay, well I don't have log base 3. I have log and ln. Now log on a calculator stands for log base 10. So you have log base 10 on your calculator. So you use this formula, you choose c equals 10 because that's the button you have. So you'd have log base 10 of 7, hit enter, then log base, then divide by log base 10 of 3. And that would be the decimal representation of log base 3 of 7 that you could actually get with the technology that you have at your fingertips. It's the same with a lot of other calculators as well. And the special case is just using a base of e. So ln, I'll talk about this in a bit, is a log function with a base of e, and e is that special number 2.71828 ... Also a button that should be on any calculator. So rule 6 is mostly for like getting decimal representations of logs. Okay, graphs. For some reason I changed it to a instead of b, but it's just any base. So we have an exponential function with a base of a, so a to the x. And if you graph that alongside the log function with the base of a, shown in blue, there's some connection between them. I'll show what that connection is in a few slides. Well, these two pairs are for a values greater than 1. So we have exponential growth function and a log function with that base larger than 1. We've seen exponential decay, that's the green one, the green curve in a to the x for a values between 0 and 1, but we don't often see the graph of a log function with a base between 0 and 1. It's shown in red there. It looks weird. It's not what you're used to seeing, but that's what it would look like. I'm going to put them both together, and also on the same graph I've graphed y equals x. Straight line, slope 1, intercept 0. What you'll notice is that the red curve and the blue curves, the red and the blue curve in the top and the red curve and the green curve in the bottom are reflections of each other. They're mirror images mirrored about the line y equals x. And you'll always find that's the case for exponential, for functions and their inverses. So a function f of x is a mirror reflection of f inverse of x about the line y equals x. We could graph y equals x squared and y equals root x and just focus on the part of the y equals x squared graph for x larger than 0. Compare those two graphs and do the same thing for y equals x cubed and y equals cube root of x. Look at those two graphs, and what you'd find is that they share that same relationship, that those two pairs of functions, which are inverse functions of each other, are reflections of each other about the line y equals x. And what I invite you to do is to use Desmos to explore this. Graph those two functions along with y equals x, and just confirm that they share that inverse, that mirror image property about the line y equals x. If you're curious, or maybe not curious, but just a reminder, something from elementary school, possibly high school, from art class, how do you reflect about a line? The way you would do that, so I'll just look at the triangle shape on the bottom left here. Say I want to take the blue triangle and get the mirror reflection of that about the line y, using the line y equals x, that diagonal line as the mirror. What I would do is I would take that point at one of the vertices and connect it up at a 90 degree angle to the mirror line. Take out a ruler, measure how long that distance is.
Sorry, I don't know how to help with that yet.
Apply that distance also at 90 degrees from the same starting point, and then that's going to be the mirror of the vertex. And do the same thing for the other two vertices of that triangle. You make sure it's 90 degrees, use a ruler and measure the same amount on the other side, and do the same for the third one. And then connect the dots, and that would be your shape. So after you've drawn the dots, get rid of the lines that are drawn in, and then connect those dots. That creates a mirror image. You could create the inverse of any function graphically. Start with a graph of f of x, draw the line y equals x, mirror it, or take a few dots and mirror those dots, and then connect the curve, and now you've created the inverse graphically, done it visually. It's very cumbersome to do that, so we tend to do them algebraically. Okay, as stated, we have log functions of any particular base b, but there's a special one, log function with the base of e, and it's special enough and useful enough, and it comes up often enough that we have a shorthand notation for it, ln. It's 2 characters instead of loge. And it's defined in the following way, that y equals ln of x if and only if x equals e to the y. So it's defined in terms of its inverse function relationship with the exponential function, base e. Rules 2 and 3, or statements 2 and 3, are the special cases of the cancellation law. Just replacing b with e. Cancellation law with base b equals e. And item 4 there is also cancellation law. I write all my lawns with a curly L. I can't stop myself. So I have it picked up at some point, I don't know when. We can write ln of e as the ln of e to the power of 1. We'll use the cancellation law. So ln of e is just ln of e to the 1, which is 1. So if you know your cancellation law, then you've automatically memorized the ln of e is equal to 1. Although it's often treated like its own special thing that you have to memorize separately, you don't. It's cancellation law. We're going to use a lot of log functions, and fortunately for calculus, most of them will be log with the base of e. We'll also use a lot of exponential functions, and also, fortunately, most of those will have a base of e as well. We'll do some other bases, but it's mostly base e stuff. Okay, and an example of constructing an inverse function that's a little bit more complicated. You can go back into Desmos and graph this function, 6 times e to the x plus 5, all divided by e to the x plus 7, and confirm that it's 1 to 1. It is. It passes the horizontal line test, and since it does, we can construct the inverse. And here's how we would do that. Our first step of constructing the inverse is to say y equals f of x. So y equals 6 times e to the x plus 5 over e to the x plus 7. Our goal is to rearrange this and get x all by itself. So it's x equals stuff with y in it. So next step, I'm going to cross multiply. Multiply both sides by e to the x plus 7. So y times e to the x plus 7 is equal to 6 e to the x plus 5. Then I'm going to distribute the y into the bracket. Y times e to the x plus 7 times y equals 6 times e to the x plus 5. Then group all the x stuff together. So I'll put all the x stuff on the left-hand side and all the stuff without x on the right-hand side. Or y e to the x minus 6 e to the x equals 5 minus 7y. So 6e to the x was subtracted from both sides, and 7y was subtracted from both sides. Next step, I'm going to common factor e to the x out on the left hand side. So I have e to the x times y minus 6 equals 5 minus 7y. And divide both sides by y minus 6. So e to the x is 5 minus 7y over y minus 6. Now we have to do an operation that I don't know if you've seen it before. Like, you've done stuff like this before, I know you have, but you may not have seen it done this particular way. When you have an equal sign, you know, if something is equal to something else, what we do with equal signs is we manipulate both sides of the expression using the same operation. So whatever you do to one side, you have to do to the other side. For example, multiplying both sides of an expression by the same thing, or dividing both sides of the expression by the same thing, or adding the same thing, or subtracting the same thing from both sides. Well, there's an operation we can do to both sides that isn't adding, subtracting, multiplying, or dividing. There's actually a whole bunch of them, and one of the new ones, is logging. We can take a log of both sides, and we can log any base that we want. But I'm going to use log of the base of e, because we have an exponential function of the base of e, and we'd be able to use a cancellation law if we use this particular base. So I'm going to take the log of the left side and the log of the right side. So the log of e to the x equals a log of 5 minus 7y over y minus 6. On the left we have a cancellation law. So we have x equals the log of 5 minus 7y over y minus 6. Now we're going to do a swap x's and y's. So we have y equals the log of 5 minus 7x over x minus 6. And our final statement is that f inverse of x is equal to the log of 5 minus 7x over x minus 6. If you wanted to, you could check this. You can confirm this is the answer by replacing every x in the original expression, in f of x, with this f inverse, ln of 5 minus 7x over x minus 6. So replacing the x on the top and the x on the bottom with that log, simplifying, using log properties, rearranging, and if you do everything right, you should get x at the end, because f inverse of f of x has to equal x, and f inverse of x has to equal x. And you don't. And let's say you want to check it, but you don't want to invest that much effort. Plug a particular x value in, like 0. Plug 0 in for x and top and bottom. Simplify, then take that output and plug it into f inverse, and make sure you get the original input back. Make sure you get 0 back. Okay, and I think that's the end of part 1. There'll be a new video for part 2.